Greetings and welcome to the Steins Institute. If you've been browsing the internet for any amount of time, you'd have stumbled upon these image files called Jpegs. They stand for Joint Photographic Experts Group. It is the name of the shady committee group that developed this file type, after years of experiments testing the limits of what our eyes can and cannot perceive. It is one of the most useful compression algorithms ever developed, and as a demonstration of its compression capability, here we have a bitmap of a Bulbasaur, raw and uncompressed, in all its wholesome glory. It's 192 kilobytes, quite large for such a small image. And here we have the same picture, except this time it is compressed into a JPEG, and it's only 19 kilobytes, a tenth of its original size. Can you tell the difference? Probably not. However, if we subtract the color values of these two images, we can see that there are indeed subtle differences our eyes can hardly detect. So how did we remove more than 90% of the content from this image and still have it look almost exactly the same? What kind of black magic is this? Well, strap in, since we'll be uncovering all the shady things done to your bitmap to compress them to an ever smaller size. But first, we need to understand how images are stored when they are uncompressed. In other words, bitmaps. As its name suggests, a bitmap maps a picture's every pixel in bits. We go down the picture top to bottom and record its color for every pixel. The color of a pixel is written in its red, green, and blue values, RGB for short, and stored in 3 bytes, 1 byte for each value. So to get the size of an image, you simply multiply the number of pixels with 3 bytes. In this case, we get 192 kilobytes, which is exactly what we expected. Bitmaps are great, because they're as simple as they can get. They're easy for a monitor to display, since each pixel in your monitor is just 3 LED in red, green, and blue. We can naturally map a byte in our bitmap to an LED in the monitor. The downside, of course, is that bitmaps are huge. They take up huge amount of disk space and occupy a large amount of bandwidth when transmitted across the internet. So how does converting a bitmap into a JPEG cut down its size dramatically? The important thing about JPEG is that it's a lossy compression format, which is to say, when you compress a bitmap into a JPEG, you lose some of the information. After the compression, it wouldn't be the same image as before, just an approximation of the original. This is achieved by exploiting the weakness of the human eyes and throwing out the useless information our eyes cannot perceive. In our eyes, we have photoreceptors called rods and cones. They detect light and send it to our brain. To put it simply, rods detect brightness and cones detect colors. We have about 20 times more rods and cones, which is to say our eyes are way more sensitive to change in brightness than it is to change in colors. And we can exploit that in our compression algorithm. To do this, we need to transform our colors from the RGB format to the YCbCr format. The Y represents luma, which is another way of saying brightness. Chroma blue, CB, and chroma red, CR, are the chroma channels that represents color. Since our eyes are way more sensitive to brightness, we'll leave the white channel unchanged, but we'll cut the resolution of the CB and CR channel both by 75%. This may seem like a drastic change, but the effect is barely noticeable to our eyes. This is the original image, and this is the image after the reduction of the CB and CR channel. You'll need to look really hard to actually spot the difference. So, with this simple trick, we already achieved 50% compression rate with almost no perceivable loss in quality. But we can go even further than this. As of right now, the picture is stored as a collection of pixels. To achieve further compression, we'll need to represent the picture as a collection of 2D cosine waves instead. This may seem confusing at first, but there is a reason for this. If you try to compress a picture by removing pixels, our eyes will immediately notice the missing pixels that are removed. However, if we remove some waveforms from the picture, our eyes will barely notice. It's the same reasoning as our previous step. We apply our transformation and then cut out the parts our eyes are not sensitive to. To do this, we first need to divide each of the 3 channels in the picture into small 8x8 blocks. We'll be processing each of these blocks individually. Each pixel in this block is represented by an 8-bit integer that ranges from 0 to 255. In the case of the Y channel, the higher the value, the darker the pixel. Now this is where things start to get complicated. We then apply a process called the Discrete Cosine Transformation, DCT for short. This process transforms the 8x8 block into the frequency domain. What we basically did is transform 64 pixels into 64 2D cosine waves of different frequencies. We'll call this new block the DCT block. We can recreate the picture by overlaying these cosine waves on top of each other. The amplitude of these waves are given by these numbers. A negative number simply means we subtract the value instead of adding it. The most important value in this DCT block is the first one. It represents the average value of the 8x8 grid. It is also known as the DC coefficient. The frequencies of these 2D cosine waves increases in the x component as we move to the right, and increases in the y component as we move downwards. These waves describe the deviation from the average value. To understand just how useful this transformation is, let's take these 9 waves given by these 9 coefficients and add them to the average value given by the DC coefficient. We get something remarkably similar to the original. So in theory, we could discard the rest of the data and still be fine. The amplitude of these discarded waves are either too low for our eyes to see, or at a frequency our eyes have trouble perceiving. So how does the algorithm decide which one to discard? This is where the quantization matrix comes in, developed by the aforementioned Joint Picture Expert Group. This is an example of a quantization matrix we use when converting JPEGs. The higher the number, the more likely the corresponding cell in the DCT block will be set to 0. What we do is simply divide each of these numbers to the corresponding cell, then round it down to the nearest integer. As you can see, if we do this, a lot of the values become 0, which means they are discarded. You may have noticed the value of the quantization matrix becomes larger as the frequency of the cosine waves increases. This means high-frequency waves are more likely to be set to 0 than low-frequency waves. This is due to the fact that our eyes have trouble perceiving high-frequency change in brightness or color. To see why this is, let's take the highest frequency waveform possible from the bottom right of the grid. This wave causes the color or brightness to oscillate every pixel. However, if we zoom out, we don't see the alternating black and white. Instead, we just see the average color given by the DC coefficient. So we might as well set the value to 0. As a side note, this is not the only quantization matrix we can use. To achieve higher compression but lower quality, we can use a quantization matrix with higher numbers, since this means more waveforms will be set to 0. The vice versa is also true. You can achieve higher quality but lower compression by making the values lower. When we use a quantization matrix with values that are too high, we may end up discarding too much information. This is when JPEG artifacts occur, and you can actually see the individual 8x8 blocks, because they no longer blend together to form a coherent picture. Alright, back to our compression algorithms. Even though we set a good amount of our coefficients to 0, to store this, we will still need 64 bytes, since it takes just as much memory to store 0 as it takes to store any other integer. To actually get rid of these zeros, we would group the consecutive zeros together and store them in one number. For example, When storing this matrix, instead of storing each of these zeros one by one, we simply count the number of consecutive zeros and store that number instead. In this case, we achieved around 50% compression. In some cases, though, when an 8x8 block have uniform color, for example this block here, where all the pixels are white, all the values of the DCT block would be 0, except for the first cell, which represents the average color. In these cases, we can achieve super high compression rate. Well, that's about it. We would perform this process for all the 8x8 blocks in all the channels, and store them in a Jpeg file along with the quantization matrix used. And we got ourselves a small compact image file ready for storage and transfer. If you haven't noticed by now, we just performed the image processing equivalent of feeding someone into a meat grinder and stuffing what comes out into a suitcase. We can't just feed this to the monitor and expect it to display it. As we mentioned before, the monitor needs the RGB value of each pixel in order to display a picture. In other words, a bitmap. So to display the image, we need to decompress the JPEG, which is to do everything we just did, but in reverse. But since some of the steps we performed are irreversible, such as when we straight up discarded more than 75% of the resolution of the CR and CB channel, or when we set a good chunk of the frequencies in the DCT block to 0, the decompressed image is just gonna be an approximation of the original. If we chose the right quantization matrix, the difference would most likely be unnoticeable. So why did we go through all this trouble of compressing the image if we are just gonna decompress it in the end and end up with an inferior copy? This is because in its compressed form, the image takes up much less storage and is much easier to transfer. At a compression ratio of 10:1, we can transfer 10 JPEGs in the time it takes to transfer one bitmap. This is especially important when we are transferring video files, since videos are just strings of JPEG. And video player is basically a decompressor that decompresses JPEG at a super high speed. Without JPEG technology, streaming videos would virtually be impossible. In our next video, we'll be talking about MPEG compression used in video files, and how it takes what we learned today even a step further. So make sure you subscribe so you don't miss out on more weekly science and technology related content.
This blue eye perceives all things conjoined, the past, the future, and the present. Everything flows, and all is connected. This eye is not merely seeing reality, it is touching the truth.